Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Masuvakalle. Today we are going to discuss the 10th session of Graph Theory 2 of first unit. Now we are going to discuss in this session the problems on Eulerian and Hamiltonian graphs. Problems on Eulerian and Hamiltonian graphs. Okay, in the previous class we have discussed so many concepts, and in that we have discussed Eulerian graph, Hamiltonian graph. Okay, even we took many examples on Eulerian graphs as well as Hamiltonian graphs. Now we see some different types of questions in this session. Let me consider first example. Give an example of a graph which is Eulerian but not Hamiltonian. Give an example of a graph which is Eulerian but not Hamiltonian. Okay, you know already the concept of Eulerian graph and Hamiltonian graph. Eulerian graph, it must contain an Eulerian cycle. That is, when a graph is Eulerian, there is a general characterization. A graph is Eulerian if and only if degree of every vertex is even. If you draw any graph, any connected graph with all even vertices, obviously that will be an Eulerian graph. Very easy to draw Eulerian graph. Now, what do you mean by Hamiltonian graph? A graph containing a Hamiltonian cycle, that is an ordinary cycle containing all vertices. You can say spanning cycle. Okay, so let me answer for this question. It should be Eulerian, but it should not be Hamiltonian. Let me consider K24, two vertices at the top, or one at the top or another at the bottom. Four vertices in between. One, two, three, four. So, what do you mean by complete bipartite graph? This vertex must be adjacent with all other vertices. Similarly, the other vertex with all other vertices. This is K24. Okay. Now, if you observe the degree of every vertex, one of the results says if degree of every vertex is even, then that graph is definitely Eulerian. So, therefore, K24 is an example of an Eulerian graph. It is an Eulerian graph. But is it Hamiltonian is the question. Okay. Now, is there any Hamiltonian cycle, a closed path, or you can say a spanning cycle, a cycle containing all vertices? Is there any such cycle? Even if I start like this, if I enter like this is only one cycle. You have not considered these two vertices. If I consider like this, if you go like this, you are unable to. Yes, of course, you reach here. It implies still it is not a complete cycle. It is an ordinary cycle. Once if you go like this, how can you come back? Because it is a closed path. Path means there is no repetition of vertex. When vertex is not repeated, obviously edge is also not repeated. So therefore, there is no any such cycle containing all vertices of the graph. Even if you try in this way, okay, you cannot repeat the vertex. It implies you cannot reach this vertex. It implies you are neglecting. So there is no any cycle containing all vertices. Therefore, this is an example of an Eulerian graph but it is not Hamiltonian. Okay. Still, as there is a characterization for Eulerian graph, so very easily we can identify it is an Eulerian graph. But still, we didn't reach about the characterization or whether there exists a characterization or not. That we have not discussed so far. That's why we are facing a problem to draw a Hamiltonian graph easily, isn't it? So that's why this is one simple example. So K24 is Eulerian, but it is not Hamiltonian. Let me consider another example. Give an example of a graph which is Hamiltonian but not Eulerian. Which is Hamiltonian, the second example. It is Hamiltonian but not Eulerian. Pronunciation, you may say Eulerian or Eulerian. It is left to an individual. So pronunciation, okay. There is no much more importance about the pronunciation. So give an example of a graph which is Hamiltonian but not Eulerian. Okay. So if you draw a graph which contains a cycle containing all other vertices, all the vertices of the graph, then obviously that will be a Hamiltonian graph. Okay. Now, if there is at least one vertex of odd degree, then you can say it is not Eulerian. It's very obvious because degree of every vertex must be even. Then only it will be an Eulerian graph. Suppose if I consider an example of a complete graph with 6 vertices. Let me draw the graph of K6. 1, 2, 3, 4, 5, 6. Now like this. You can try to draw K6. It is a complete graph with 6 vertices. Yes. It is a complete graph with 6 vertices. What do you mean by complete graph? Every pair of vertices are adjacent. Okay, so we got a complete graph. And we know that every complete graph Kp is P minus 1 regular. What do you mean by a regular graph? A graph is said to be regular if degree of every vertex is same. Okay, so every complete graph Kp is P minus 1 regular. It implies it is K6. So K6 is P minus 1, that is 6 minus 1, 5 regular graph. It implies degree of every vertex is 5. You can count 1, 2, 3, 4, 5. Similarly, here also 5, 5, 5, 5. So degree of every vertex is 5. So now is it a Hamiltonian graph? Okay, V1, V2, next there is a cycle containing V1, V2, next V3, next V4, V5, V6, and again we have retest back to V1. Yes, there is a cycle. There is a cycle containing all vertices of the graph. So that cycle is called Hamiltonian cycle. So any graph which contains a Hamiltonian cycle is called a Hamiltonian graph. So therefore this is an example of a Hamiltonian graph. Now, is it Eulerian is a question. So when you will say it's an Eulerian graph, degree of every vertex must be even. But here K6 is 5 regular. It implies degree of every vertex is 5. It implies every vertex is an odd vertex. Even if there is at least one vertex of odd degree, it will not be an Eulerian graph. So therefore, obviously what you can say, though it is Hamiltonian graph, but not Eulerian. This is an example. So K6 is Hamiltonian, but not Eulerian. Okay. So let me consider the third example. Give me one example or give an example of a graph which is Eulerian and also Hamiltonian. Okay, Hamiltonian and also Eulerian. Okay, both Eulerian as well as Hamiltonian. So what would be the answer for this question? Can you guess? Give an example which is both Eulerian as well as Hamiltonian. I think you are thinking in your mind. So graph theory always leads you to think. It makes you to think. Every step, every moment, you are thinking something. So that's why this is very interesting subject. It makes you to think. This theory makes you to think. Very simple example you can give, of course. C5, any cycle, say C5. It doesn't mean that you have to consider the same graph which I have considered. You can think and you can draw your own graph also. So this is the graph C5. So C5, there is a cycle containing all vertices. So therefore, it is Hamiltonian. And whether it is Eulerian, definitely degree of every vertex in a cycle is 2. So therefore, every vertex is an even vertex. So therefore, degree of every vertex is even. So it is Eulerian. So it is both Eulerian and Hamiltonian. So this is an example of Eulerian as well as Hamiltonian. So it implies every cycle Cn where n greater than or equal to 3 is definitely Hamiltonian as well as Eulerian. But how about the complete graphs? Amongst the complete graphs, which complete graphs are both Eulerian as well as Hamiltonian? If that would be the question. Amongst the complete graphs, which complete graph is both Eulerian as well as Hamiltonian? As I said, if that would be the question, as I said, every complete graph Kp is p minus 1 regular. Okay, if both must be Eulerian as well as Hamiltonian, it implies, of course, in a complete graph there is a cycle containing all vertices. So every complete graph Kp where p greater than or equal to 3 is obviously Hamiltonian, because to form a cycle we require minimum 3 vertices. So every complete graph Kp with at least 3 vertices is definitely Hamiltonian. But out of those complete graphs, which complete graph is Eulerian? So this should be even. This should be even. So p minus 1 should be even. So p minus 1 should be even. It implies p should be odd. If p is odd, k n, where n is odd, or you can say in the form of you can say n plus 1, where n is greater than or equal to 2. So it may be 3. I think not n plus 1. It is 2n plus 1. 2n plus 1. 2n plus 1, where n is greater than or equal to 1. So that should be the standard one. Because if n is 1, it will be 3. If n is 2, it will be 5. Okay. If it is a complete graph with odd number of vertices, then degree of every vertex will be even. Then it will be an Eulerian graph. Okay. I hope you have followed. So, which complete graph? A complete graph with odd vertices contains even degree. Then it will be an Eulerian graph. So, in that way, if you think, so those are the complete graphs with odd number of vertices will be Eulerian. So it should be 2n plus 1, where n greater than or equal to 1. Okay. In that, if I consider K3 is a complete graph with the 3 vertices. So this is an example of K3. Then if I take 2, it will be 5, K5. Yes, this will be our K5. Yes, K5. Here degree of every vertex is 4. So that it will be K, I think 3, if I give 3, 7, K7. So degree of every vertex in K7 is 6. So that is even. So it will be an Eulerian graph. So this is how amongst the complete graph also you can bifurcate. All complete graphs with a p greater than or equal to 3 is obviously Hamiltonian, but only with odd vertices. So complete graph with odd vertices that too it should be greater than or equal to 3 will be an Eulerian graph. Okay. So in this example, we have considered one more example while discussing K5. Okay. Let me consider another example. Give an example of a connected graph which is neither Hamiltonian nor Eulerian. Okay. It may be fourth or fifth example. Neither Hamiltonian nor Eulerian. Should not be Eulerian, should not be Hamiltonian. So like that you have to give an example. So what would be the graph? Again, you just think, and according to your thinking ability or according to your choice, you may draw a graph which is neither Eulerian nor Hamiltonian. As far as me is concerned, okay, this could be one example. Okay, if I consider this could be an example of a graph which is neither Eulerian nor Hamiltonian. Okay, is it Eulerian? Obviously, there is one vertex. Of course, there are two vertices of odd degree. If there is at least one vertex of odd degree, it will not be Eulerian. It is not Eulerian because there is a vertex of odd degree. Is it Hamiltonian? Is a question. There should be a cycle containing all vertices. If I start like this, if I go back like this, you are not considering this vertex. Means there is no cycle containing all vertices. This is not a cycle containing all vertices. If I reach like this, okay, then how will reach to the starting point? Where is the way? Where is the way? You cannot go back because there is no repetition of vertex. Obviously, there is no repetition of an edge also. So there is no cycle containing all vertices. There is no cycle. Even if you start with this, like this, like this, like this. Okay. Now you may reach like this, but there is no option to come back to the starting point. It implies this is neither Eulerian nor Hamiltonian. This is an example. So this is how they ask such examples in the examination. So it may be Eulerian as well as Hamiltonian. One is Eulerian, one is Hamiltonian. One may not be Hamiltonian, or one may be Hamiltonian, another may not be Eulerian, or both may not be Eulerian as well as Hamiltonian. So such questions we have discussed in this session. Okay. In the next session, we will discuss, as we have got a general result to characterize the Eulerian graph, is there any such characterization in the Hamiltonian graph? See, the concept of Hamiltonian graph, very simple. A graph is said to be Hamiltonian if there is a Hamiltonian cycle or a cycle containing all vertices, or you can say a spanning cycle. There must be a spanning cycle. So concept is very easy to understand. Is there any characterization for Hamiltonian graph? That we will discuss in the next class. With this we conclude. Thank you.